Imagine a future where industries no longer contribute to climate change but actively combat it. How does that sound? Assalamu alaikum everyone. My name is Zubair Rasmin Sikdar. As the first presenter, I am more than delighted to demonstrate our paper. It is an honor to present our paper titled Forecasting of Carbon Dioxide Emissions and Optimal Selection of Carbon Storage based on distance, cost, and capacity metrics with a data-driven pipeline. Our research explores how machine learning can optimize carbon capture and storage, transforming carbon dioxide from an environmental threat into an opportunity for sustainability. This is not just a vision, it's a reality we are working towards. This research applies data science methods to model country carbon dioxide emissions while determining suitable storage sites through determination of geographic location along with economic data factors. The emerging power of machine learning enables better CCUS operation by using big data to improve carbon capture systems and identify optimal storage locations while reducing operational costs. Our goal is to predict carbon emission and suggest storage sites for any country. As a global carbon dioxide emissions continue to rise, addressing climate change has become more urgent than ever. Our research focuses on developing a predictive system that not only forecasts carbon dioxide emissions but also identifies cost efficient and strategically optimal carbon storage sites. By integrating historical emission data with geospatial and economic factors, we aim to enhance the effectiveness of carbon capture and storage strategies globally. We use 6 time series models forecasting carbon dioxide emission after pre-processing datasets with normalization and 80-20 chain test split, and the model with least may was selected, in which storage sites are used to store in considering distance, cost, and storage capacity using MCDA methods as a scientific way of extracting output. To visually show output, we use Power BI. Our analysis shows that by LSTM stands out as the best model for creating accurate emission predictions. Besides, the study combined historical emission records with CCS project data as well as economic and geographic characteristics to discover ideal storage sites for captured carbon. We primarily made such contributions as the creation of a site selection model based on CCS map 2023 with cost, capacity, and distance parameters through MCDA techniques, then created of an interactive Power BI world map with site metadata, also converted all cost in USD to understand all the expenses better with the incorporation of distance factors to effectively perform the unified analysis. Lastly, we have completed CCS map data datasets combustion separation column, which was one of the crucial incomplete columns in our dataset that helped us to successfully fill the data gap and made the analytical dataset more absolute. We have read many papers, but these two papers inspired us the most. We use three datasets here: CCS map dataset, our research drive data from National Energy Technology Drive Laboratory Carbon Capture and Storage Database, which holds worldwide data regarding CCS operations, historical emission dataset, the climate analysis indicator tool supplied this dataset, which tracks carbon dioxide emissions across 195 countries and regions from 1990 to 2018. This dataset comprises 34 columns, which include dark variables, country, along with sector and gas parameters, and unit measurement alongside yearly emissions data. Distance dataset. The distance dataset enables carbon dioxide storage and trapping research by analyzing 50,176 country pairs throughout 14 specified key variables that detail their social, economic, and graphical interconnections. This helped us rank and suggest the best storage locations based on distance and cost. To ensure the currency and accuracy and performance of our models, we built a structured pre-processing pipeline. For the first step, cleaning and restructuring, we excluded the top row, which represented world level emissions and any null and inconsistent values to ensure data integrity. For the second step, normalization with min-max scalar, we scaled values between 0 and 1, ensured countries with very high emissions didn't overpower the training process, and improve computational efficiency and model convergence. For the third step, train test split, we divided the dataset into 80% training, then 20% testing and validation. This ensured enough history for learning while keeping the test set unbiased. Lastly, the values missing in the column of combustion separation are filled using the assistance of the rule-based interference process relying on the unknown types of CCS engineering. Now I am passing the floor to Antor.
Thank you, Nubaira, for passing me the floor. Hello, everyone. I'm Emilul Siddiq. Now, I would like to present our overall work plan. So, from our three datasets, we used historical emission dataset at first, after dataset pre-processing step. It takes input from the user as country and prediction year. 6 time series models were trained and used for carbon dioxide emission prediction. Then, using the least may among the models, we choose the best prediction. After that, CCS map dataset alongside country-to-country distance dataset, we came up with a dataset where plant location to input country distance are calculated and all the costs were converted to US dollar. Then our initial approach was, after checking some constraints like cost, distance, storage capacity, existingness, and if the input country is different from the plant location, then the plant type has to be international. We came up with 3 plant details with nearest distance, 3 plant details with lowest cost, 3 plant details with maximum storage capacity. But it was not precise to one output, so we used MCDA techniques, including TOPSIS, FICOR, and WSM, and all techniques gave us one plant details based on the cost and distance. We choose TOPSIS as output as our final output, as all the methods are giving the same output. Going forward to our next slide, we used LSTM because it can capture long-term dependencies in time series data. It can handle vanishing gradient problem. It can maintain information over long sequence through call state. Here we had to use a recursive function which was adding predicted emission to our main data until it reaches the target year. We choose BiLSTM for its similar architecture to LSTM but bidirectional. In BiLSTM, we used recursive function as LSTM. We choose GRU because it's a simplified version of LSTM which takes less parameter than LSTM, has faster training, and also good for shorter sequences. Similar to LSTM and BiLSTM, we had two recursive function as well as in GRU. We used our traditional time series model. We used ARIMA as it uses past values, past errors, and makes data stationary. SARIMA adds the seasonality feature into it. We have used our Facebook Prophet model. We used it as it can handle missing data and can automatically detect seasonality. We used Prophet model in a such way so it can predict emission up to target year or input year. In the next slide, here we have performance metrics MAE, MAC, RMAC, and R square. As we know, lowest MAE, MAC, and RMAC represents better model, but in the case of R square, we know higher value means better performance. Here we got the best score based on input as 4 countries and prediction year as 2026. In all cases, LSTM, BiLSTM, and GRU performed better, and Prophet was not worst among all. Going to the next slide. Here we analyzed our model performance based on the previous parameters of 4 input countries, where mostly Prophet and SARIMA performed bad. In the next slide, here it is about training loss and validation loss of LSTM, BiLSTM, and GRU. The graph shows our models are trained and fitted well with the dataset. We used 80% data for training and 60% for validation. Now I would like to pass the floor to Mithila to present. Thank you, everyone.
Thank you, Antor. Hello, everyone. I'm Janatul Firdaus Mithila. As the final presenter, I will briefly summarize our key results, strong storage decision framework, visual outputs, and the limitation and future scope of our work. Our goal was to create a practical pipeline that helps countries to predict CO2 emission and plan cost effective carbon storage using data driven method. We use six forecasting model to predict 2026 carbon dioxide emission for random input countries Bangladesh, Sweden, and China. The model with the lowest MAE was selected because it best represent average real world prediction error. As shown in the result here, China's emission is the highest compared to Bangladesh and Sweden. Next. As shown in the graph, these are the input three countries' emission trends in here. LSTM consistently produce the most accurate prediction by effectively capturing long-term emission trends. Next. After prediction, we applied multi-criteria decision analysis using TOPSIS, WSM, and VCOR. This method jointly consider cost and distance, allowing trade-off between criteria instead of simple ranking. All these three MCDA methods selected the same base storage site for each country, increasing confidence in the final decision. Next. This slide presents a detailed MCDA-based storage for input country Bangladesh using post-combustion capture. The table shows project ID, project name, location, and exactly distance from the location country Bangladesh, and precise location using longitude and latitude, and the cost. Consistent result across all these three MCDA method confirm that the selected site is reliable and not dependent on one single ranking technique. Next. To improve our usability, we develop an interactive Power BI dashboard for each sketch. Only the final recommendation storage site is highlighted here, and clicking it or selecting it reveals all the technical and economic details. This design makes the output easier to interpret and more useful for policymaker and decision makers. Next. Our study present an integrated framework combining machine learning based emission forecasting with optimized carbon storage planning. BioLSTM achieved the best accuracy using MAE, with MCDA ensured the practical and cost effective site selection by integrating emission, cost, distance. Our framework support data driven CCUS planning aligned with global climate goals. Next. Our work faced few limitations, including unit conversion inconsistencies across dataset, missing air volume data for high-risk level estimation, exclusion of zero-cost project to avoid bias, and limited hyperparameter optimization due to computational error. This factor restricted depth, but we believe that not to the overall validity of the framework. Next. Future improvement include multivariate emission, modeling risk threshold and alert system, online forecasting dashboard, and integration with government or UN climate dataset. We believe that with richer data and stronger computing resources, this pipeline can evolve into a scalable, real-world CCUS decision support system. Thank you everyone for being with us.